Hello again. I'm back with another video. This time the video is related to thermal deformation and compressive load that in this particular problem is going to be generated as a result of the gap closing due to raise in temperature. So you see here we have a square bar number 1 that has actually a cross section of 2.5 by 2.5 inch. So this section here that you see is a 2.5 by 2.5 here. That's a cross section. Okay, so this material is a high density plastic that, let's say, has a modulus of elasticity, so this is given, of 120 KSI. And also we need the coefficient of thermal expansion, alpha, which for this particular material is 78 times 10 to the negative 6 per degree Fahrenheit. And you see the original length of this bar at room temperature is 32 inch, and the gap here is 0.1 inch. So what we want to find is, we want to find the compressive load that is developed when we raise the temperature, delta T is 100 degree Fahrenheit. So in other words, if the room temperature is 70 degree Fahrenheit, what if now the temperature is 170? Raising the temperature by 100 degree Fahrenheit, what load will be developed? So you see, obviously, what will happen is that this gap will close, and actually what will happen is that if there wasn't any constraint, this will probably expand beyond 0.1, and then because there is a constraint there, then what load needed to bring it back to that where the support is, the ceiling is. That's what we are trying to determine. So this is really a very easy problem to do. So we know that we can actually calculate how much thermal deformation we can get for this bar whose length is 32 inches. So in other words, if there wasn't any constraint, there wasn't this rigid, structure here, and we let bar 1 expand due to temperature increase, what would be the thermal deformation? Well, that happens to be based on this formula, L, the initial length, times alpha, the coefficient of thermal expansion, times delta T. Sorry, I just have to erase this and change this to, I put delta T. Okay, that's raising temperature. All right, so let's go ahead and plug in. So we have 32 inches. We have an alpha of 78 times 10 to the negative 6 per degree Fahrenheit. Let's keep track of the units, and times 100 degree Fahrenheit. So you see how Fahrenheit and Fahrenheit cancel. So we end up getting our increase in temperature, or thermal deformation, denoted by delta T, as 0.2496 inches. So that's clearly beyond the gap. So let's see what's the difference between this delta T and the gap. So whatever the difference is going to go into what we call a deformation. So this is basically your delta P. I can draw another picture here for you. So here's the bar, right? Here's the gap. So when temperature rises, so this is the gap here, which is 0.01. When the temperature rises, this is going to go up to here if there wasn't any constraint here, right? So this is your delta T, and if you now get the gap from the delta T, that would be delta P. So this is basically your delta P. This. So delta P in this case would be 0.2496 minus 0.1, so that's 0.1496 inches. And what is delta P? Delta P can be calculated based on this equation, axially loaded member. So if we solve for P here, P becomes EA over L times delta P. So it's just a quick plug in. So actually we can keep, E in KSI, that's fine. Area would be 2.5 times 2.5 or 2.5 squared divided by initial length of 32 inches and then a delta P of 0.1496 inches. So P comes out to be actually in kip. So the compressive load that is developed in this bar would be about 3.506 kip, or 3,506 pounds. Now, if you are interested to even calculate the thermal stress that is developed, you could actually do that by taking this load and divide by area. So if you do that, for example, take the 3.506 kip and divide it by 2.5 inch squared, the outcome would be about 0.561 KSI or 561 PSI. Okay, I hope you like this video, and I'll come back with more videos for you. Again, as always, thanks for watching and listening.